Hey everybody, I got a question about impulse functions and exactly what they are and how to use those within an integral. So typically an impulse function is something that we use to model putting a source of energy into a system right at a certain time, usually at time equals 0. So if we drew a picture of it, here's the time axis. It would be a spike, and the spike is actually infinitely high and occurs at 0. So you may think, geez, what is that? I've never seen a function like that. And it's true that it's not mathematically well defined. Mathematicians would have some trouble with this, but as engineers, we can get by with a little less rigor and still get good results. Okay, so in the videos, Professor Miller had talked about a limiting case of an impulse function. So start with something that looks like this, that has, it's centered at 0, has a width of delta, so let's go minus delta over 2 to delta over 2, and then it has a height of 1 over delta. Okay, so if I did this, and I called this function delta of t, okay, if I did this and I integrated 1 over delta of t, tau, d tau, from minus infinity to infinity, well, this thing is 0 from minus infinity to delta over 2, then it's 1 over delta, and then it's back to 0. Okay, so the area would be the area trapped underneath the curve here. So the width is delta, and the height is 1 over delta. So the area trapped on the curve would be 1 over delta times delta, which is 1. Okay, so now use your imagination. What would happen if you took the limit as delta shrinks down to 0 of delta of t? Okay, you would get something that starts to be infinitely high, but yet the area underneath the curve is 1. Okay, so that leads to the question of the homework, where we were looking at h of t being an integral from minus infinity to infinity of e to the, I don't remember exactly what it was, but let's call it, let's say we had g of t is e to the minus t u of t. Okay, so if we had e to the minus t u of t, then h of t would be, according to the convolution integral formula, it would be g of tau delta of t minus tau d tau, which is the same thing as integral from minus infinity to infinity g of t minus tau delta of tau. You have a choice on which way where you put the t minus t. In this one case, I put the t minus t on the delta function. On the other case, I put it on the g function. Okay, so now when you do this integral, delta is 0 everywhere except at tau equals 0. Okay, so you plug in tau equals 0, and you get back the answer is 1 times g of t minus tau at tau equals 0, which is g of t. Okay, and so g of t was, in this case, e to the minus t u of t. Okay, so that's the mathematics behind that, and I think that we're in danger of getting into the weeds here. So if you don't understand every detail about that, that's okay. Just hang in there with me. We'll keep working on using signals and later Laplace transforms, and hopefully we can tie this back into some meaningful reality.